We're going to look at the thermal equilibrium and specific heat practice worksheet. We're going to go over the solutions for this worksheet right now. Question number 1 on the worksheet says, what mass of water will change its temperature by 3 degrees Celsius when 525 joules of heat is added to it? The specific heat of water is 4.18 joules per gram degree Celsius. So the first thing we need to do, well, let's get that right. The first thing we need to do is solve Q equals mc delta T, and we need to solve it for mass. So in order to solve it for mass, what we have to do is divide both sides by C delta T, like that. Then C cancels, delta T cancels, and it leaves us with mass is equal to Q divided by C delta T. Then we substitute in, we get mass is equal to, we plug in our answers, or pardon me, our givens, 525 joules, divided by, the value for C is 4.18 joules per gram degree Celsius. Apologize for the bad handwriting. And also the delta T, which is 3 degrees Celsius. When we take these numbers and we take the 525 divided by 4.18, also divided by 3, we end up with 41.9 grams. It's a G, not a J. In the next question, we have 100 grams of 4 degrees Celsius water is heated to 37 degrees Celsius. Specific heat of water is 4.18. Calculate the amount of heat energy needed to cause this rise in temperature. Well, this is just a very simple Q equals mc delta T problem. mc delta T. Just substitute in the values. We have 100 grams of water. I left off the extra significant figure there. Times 4.18 joules per gram degree Celsius. And the change in temperature from 4 to 37, delta T is equal to TF minus TI. So it's equal to, that's an I, equal to 37 minus 4. So that's equal to 33 degrees Celsius. 100 grams times 4.18 joules per gram degree Celsius times 33 degrees Celsius. Grams and grams cancel, degrees Celsius and degrees Celsius cancel. It leaves us with joules. And the answer is 13,794 joules. Way more significant figures than were given to us. Really, our number here only has 3. So an appropriate answer for that really is about 13,800 joules with our significant figure rules. But you know me, I'll take that, no problem. Just don't give me any decimals after that. How many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius up to 55 degrees Celsius? The specific heat of aluminum is about 0.90 joules per gram degree Celsius. So in this case, what we're doing is we're, again, solving Q equals mc delta T. We just substitute in our numbers. We have 10 grams for our mass. C is 0.90. Again, units are joules per gram degree Celsius. And our temperature change, delta T, that's 55 minus 22, and that's equal to 33 degrees. So we plug in our 33 degrees Celsius. And when we do all of this multiplication, first of all, grams and grams cancel, degrees C and degrees C cancel. It leaves us with joules. We multiply all of this out. We end up with 297 joules. Again, with significant figures, 300 joules, with that being significant, or 3 times 10 to the 2, 3.0 times 10 to the 2 joules. Any of those answers would be sufficient. Right there is the answer that we've given up there. All the answers are, of course, on your worksheet. That's so that you can set up the problem and see if you get the same answer. If you don't get the same answer, then you set it up. The next question, question number 4. This is a little bit more difficult problem. In this question right here, what you've got is 250 grams of solid copper at 90 degrees C, that degree sign is messed up, is dropped into 100 grams of water at 0 degrees Celsius. It does say water and not ice, so we're not having a phase change or anything, but just cold water. What is the final temperature of the copper and the water if the specific heat of copper is 0.387? Water is, of course, 4.18. I'm not going to repeat that over and over again. The main thing to understand here is that Q for the water, the temperature that or the heat that goes into the water, is equal to the heat that comes out of the metal. So we can just substitute in mCTF minus Ti for the water is equal to minus mCTF minus Ti for the copper. And all of these on the water side are unique to just the water. The mass of the water right here is the 100 grams of water. The C for water is 4.18, and the Ti for water, the initial temperature for water, is 0 degrees Celsius. For the metal side, this mass is the mass of the metal. The C is the C for the metal, and the Ti is the Ti for the metal, which is 90 degrees C. The only one that is the same on both sides, the final temperature, that's what we're solving for, and it will be the equilibrium temperature, the temperature that both the metal and the water are when they achieve that balance that is called equilibrium. If we substitute these numbers now, I'm going to do this for the water. We start off with 100 grams of water times the C for water, which is 4.18. I'm going to leave off the units here just really for purposes of space, because I don't have much space on this iPad. The TF, of course, is unknown, minus Ti for the water. The initial temperature of the water is 0 degrees Celsius, is equal to the minus of the mass of the metal. It's 250 grams times the 0.387, so 0.387, TF minus the initial temperature of the metal is 90 degrees C. Getting a little complicated to write this on this iPad, but we can solve these with our calculator. We get over on this side 418 TF is equal to minus 96.75 TF minus 90. So 418 TF is equal to minus 96.75 TF. And now the minus sign and the multiplied by minus 90 when we distribute this becomes a plus, and that is 8707.5. So now what we have to do is we have to get all of the TFs on both sides. So I can add 96.75 TF to both sides, like this, 96.75 TF. I'm running out of room. See if I can make a little more room. You're going to have to remember what this says up here. I'm going to move up just a little bit. So, see here, this right here becomes 514.75 TF, I'm just going to write T, is equal to 8707.5. We continue this, divide both sides by 514.75 and divide this side by 514.75. This cancels and we get T is equal to 16.9 degrees Celsius. So our final temperature is 16.9 degrees Celsius, and Let's scroll back up and see if that agrees with what we said. 16.8. So we got some rounding error in there. But you can see that we set this up correctly. So the way we do this is we start off by setting the Q for the water equal to Q for the metal. We substitute in all the values we know for the water, all the values we know for the metal, leaving TF alone since that's the unknown. We have to be, unlike many times, we have to be very careful about our minus sign here because this is heat leaving. And the fact that our delta T, which normally we just write delta T in here, right? Delta T for the water and delta T for the metal. Delta T is split up into the TF and TI, and we have to be very cautious about these minus signs and get them in the right order. It's a common mistake to take the big number minus the little number, but in this case, particularly for the metal, remember the metal is cooling off, so it actually goes from its final temperature minus its initial temperature to get the delta T. So these minus signs are very important. If we don't do that, then when we're down here and we have to add numbers to both sides and move them over, we're going to be moving the wrong numbers and we're going to end up with the wrong answer. Which again, 16.8, 16.9. All right, the next question here is a relatively straightforward question. It's fairly simple. We have 20 degrees, or 200 grams rather, of water at 80 degrees Celsius, again, degree sign messed up, and 1,000 grams at 25 degrees Celsius, and what's the final temperature? Well, we know that the number has to be somewhere between 80 and 25. So now with this, again, when we, just like in the test review that we did, when we mix water together, we don't have to do the Q equals MC delta T equation because C for water is the same for each container of water. When we mix them together, they cancel out. What we end up with is a weighted average. So the equation, the mass of water 1 times the temperature of water 1 plus the mass of water 2 times the temperature of water 2 is just equal to the final mass, which is M1 plus M2 times T3 or T final. We can substitute the grams of water for liters of water, or liters of water for grams of water, because we know that the proportions are always going to be the same. The density of water, of both waters, is essentially the same, neglecting temperature differences. So volume and mass are interchangeable in this case, especially since the only other unit with mass in it, which is C, canceled and went away. So let's go on and do these calculations real quick. I have 200 grams of water times 80 degrees Celsius plus 1,000 grams of water times 25 degrees Celsius. It's a degree sign. So I've got this number plus this number is equal to 1,200 grams of water times that final temperature. When I multiply these out, I end up with 16,000 right here plus 25,000 is equal to 1,200 times our final temperature. I add these two together, 16,000 and 25,000. That's 41,000 is equal to 1,200 TF. So I divide both sides by 1,200 and I get TF is equal to 41,000 divided by 1,200, which is equal to 34.2 degrees Celsius, which is the answer we had up here. It's always nice when they work out. Number 6. Again, this one is just like number 4, which we've already seen. I'm going to go on and write the equation that we came up with for number 4, and we have MC TF minus TI, and this is for the water, is equal to minus MC TF minus TI for the metal. When I do my substitution for my water, I have 50 milliliters of water, and at standard temperatures, water is about 1 gram for every milliliter. So I'm just going to substitute 50 grams of water for 50 milliliters times the C for water, which is 4.18 joules per gram degree Celsius. I'm going to forego writing units on this again because of space limitations. That's equal to the final temperature minus the initial temperature of the water, and the initial temperature of the water was 20 degrees Celsius. That's going to be equal to the negative, because it's coming out of the metal, 2.2 kilograms of gold is the same thing as 200 grams, times the C for gold is 0.129 joules per gram degree Celsius, there's a decimal point in there, times TF minus 60 degrees Celsius. It's getting hard to read, I know. So this is 209 times TF, that is an F, minus 20 is equal to 25.8 times minus 25.8, don't forget that, TF minus 60. Now I have to distribute these numbers. So I have 209 TF minus 4180 is equal to minus 25.8 decimal point TF. Now the two minus signs that we have here, this minus and this minus, they cancel each other out to be plus 1,548. Now what we have to do is we have to get all the TFs on one side. So I'm going to add 25.8 TF to this side so that they cancel. I have to do the same thing over here. 25.8 TF. It's a decimal point. I also want to get this guy over to the other side, so I'm going to add 4180 to both sides. I get 5728 is equal to, draw a line here, 234 TF. Now we can just go on and solve it. TF is equal to 5728 divided by 234. That's 234.8. I forgot to put that 0.8 in there. Go back and do that. And that is just equal to 24.395. We'll call it 24.4 degrees Celsius. Let's go back up and check and see if that agrees. 24.3. I had 24.39. So 24.4, well within our rounding and significant figures. But you see how we did this? We just came up and solved this equation right here for TF. The final temperature being the same on both sides, because once the gold and water are in equilibrium, the final temperature will be the same. We have to make sure that everything on this side of the equation is related to the water, and everything on this side is the metal. And this is true whenever we mix two substances that are that have a different value for C. Our next page, in order to cool our coffee, which is a mass of 200 grams and a temperature of 60 degrees Celsius, Melanie pours 50 grams of water at 10 degrees Celsius into the coffee. What is the final temperature of the mixture? Again, this is just a weighted average. Pretty simple to solve. M1 T1 plus M2 T2 is equal to M1 plus M2 times T3 or T final. So let's go on and substitute these in. We have 200 grams times 60 degrees plus 50 grams times 10 degrees. I should use my degrees Celsius in there, shouldn't I? Is equal to, well, 250 grams, 200 plus 250, or 200 plus 50 is 250, times our final temperature. This number right here is 12,000 plus 50 times 10, that's 500, is equal to 250 TF. So 12,500 is equal to 250 TF. TF is equal to 12,500 divided by 250, which is equal to 50 degrees Celsius. It's only coincidence that it dropped by 10 degrees and she put in 10-degree water, just in case anybody was likely to point that out. It's really just this weighted average. Okay, so the 50 grams of water dropped the temperature by 10 degrees Celsius. The last question on the worksheet, number 8, a 15.75 gram piece of iron absorbs 1,086.75 joules of heat energy, and its temperature changes from 25 to 175 degrees Celsius. Calculate the specific heat capacity of iron. So, in this case, we start off with the equation Q is equal to mc delta T, and we need to solve this for C. So I'm going to divide both sides by m and both sides by delta T. Then we can get rid of the delta T, and we got just C. So C is equal to Q over m delta T. So let's come down here and solve it. So C is equal to 1086.75, that's joules, divided by, the mass is 15.75 grams, and the temperature change, well, here we need to look at the temperature change. Delta T, the final temperature is 175 minus the initial temperature, which is 25 degrees Celsius. So the change in temperature is 150 degrees Celsius. So that is positive, by the way, since we're warming it up. 150 degrees Celsius. If heat was going out, then both the Q and the temperature change would be negative, and we would still get a positive C. When we take this number and do the math, we end up with 0.46, and if we look at our units up here, we have joules, we have grams, we have degrees Celsius, nothing cancels, so it's joules per gram degrees Celsius. Now I noticed that up here they put 3 significant figures, and they gave us 4 here for the mass, and they gave us 6 significant figures here. When we look at these numbers here, like 175, that looks like 3, and this looks like 2. In reality, however, let's go back to this. This number 25, if we were to look at this in Kelvin, this is 298 Kelvin. So when we measure a temperature in Celsius, we can actually treat it as if it were a Kelvin number. And there are 3 significant figures here in the value 298 Kelvin. So we actually do have 3 significant figures for our temperature, even though we're only showing 2 digits. And this confuses a lot of people in chemistry as well as physics when they're doing significant figures. Always do your significant figures from a perspective of Kelvin, and then you'll know how many significant figures you actually have. If you have decimals after your degrees, then you could actually go to 4 significant figures in this case. But 25 degrees by itself has 3, 175 has 3, and in reality our answer, 150, down here for our delta t, there are 3 significant figures. That 0 is significant in this case. And this is our change in temperature in degrees Celsius, or our change in temperature in kelvins, 150 kelvins. It's the same thing because the spacing between degrees in Celsius and Kelvin is exactly the same. They just have a different starting point. So our final answer right here, we could actually have that extra significant figure. It is justified. So 0.460 joules per gram degree Celsius is our calculated value for the specific heat of iron given the data we have here. And that's it for the worksheet. I hope this has been informative. If you had any trouble achieving the answers that are given at the end of each of the questions, then go back and check your work. Make sure that you set them up correctly. If you still had trouble, then I would suggest you check your order of operations. One of the biggest problems that I've seen in order of operations is when you take a number like this one right here, the 1086.75, and then you divide it by the 15.75, which is correct, but then you multiply by 150, and that's not correct. That's wrong. It's 1086.75 divided by 15.75 and also divided by 150. This is below the line here, which means you need to divide by 150 just like you divided by 15.75. The only way to put a multiplication sign in here, if you wanted to multiply these, you'd have to put parentheses around both of these numbers first, because if you don't do that, then when you multiply, you just moved this number up to the top. You just moved the 150 up to the top. So just remember, if it's below the line, divide no matter what. So the 1086 divided by the 15.75 and also divided by the 150. If you multiplied by 150, you got the wrong answer. That's where the biggest errors come from. If you have set it up correctly and are still getting the wrong number, that's probably what you did. That's what I see the most. Good luck, and see you for the test tomorrow.